Yes, thank you. And thank you to the organizer for inviting me. This is a joint work with Nicolas Meunier and Raphaël Roux. And first I will try to introduce the topic, then I will present the convolution case, and I'll try to show how the convolution case can be related to the non-convolution case, and you'll see this is the most, let's say, physically sound model between both. And then I will just give some numerical tests at the end and some conclusions and open problem. Basically I will consider this equation, which is a kind of stochastic equation, which has the particular memory term here, the integral term. So here what you can see here is the distance between, so x is of course a position of a particle, xt minus xs is some kind of distance with some past position, and I will weight this distance with some kernel that will account somehow for the time, the age of this specific distance. And you see that according to the sign of alpha, if alpha is negative, then this term plays the same game as the time derivative, basically. And if alpha is positive, he is against the time derivative. So basically, we have a repelling force if alpha is positive, and attracting force when alpha is negative. Okay. So where does this model come from? So basically, there is a lot of okay, and it's the kernel can be either scalar or a matrix kernel. It does not play any role here. And so basically, what the model describes is, for instance, some memory effect of a predator, for instance, that does not want to visit sites that he already visited. So you might include some kind of avoidance of past position or past trajectories. And so what we will see during the talk is that the main ingredients of qualifying the behavior of the solution is basically the alpha constant and the first moment of rho. That basically this will be the key quantity that will drive the behavior of the solution. And so basically, where does this come from? In the probabilistic setting, one of the first paper is by Duret and Rogers, who made some kind of assumptions of the behavior of the solution when time grows large. And they made some conjectures, and during the past years, people often try to show these conjectures. So what you should notice here is that there is a kind of derivative of a potential. So f here might be seen as the gradient of some function. Basically, the behavior of f is often decreasing, so that basically you say the longer the distance you have to consider, the smaller the contribution. So here we don't exactly adopt this setting, because to our concern it was, let's say, already the linear case was interesting, and so here, if I just sum up, in the probabilistic setting, people play with different behaviors of f. And here we added, we took f to be linear and we added some kernel, okay, which is also another way to account for, let's say, larger distance. If you say that the further you go in the past, often the further you are, basically. So it's another way of weighting long distance, if you want. And so in the deterministic setting, in the field of blood flow, so cell adhering to the walls of arteries, there are also some kind of simplified models that were considered by Nicolas Meunier, and they made a lot of asymptotic behaviors of asymptotic description of the solution in the nonlinear case, but in the attractive case. So when psi is a convex function, you see that it's the attractive case. And in this case, we already did some kind of theoretical analysis of the asymptotic behavior of solutions. And so here, what I will present briefly is some kind of, in first step, formal results when, according to the value of the product alpha, the first moment of rho, the kernel, you will have either a Brownian motion or a critical regime when the expectation behaves like a kind of super diffusion. And in the supercritical case, there is a kind of positive eigenvalue and the solution blows up. And so basically this will be the three different cases that I will consider. So I will just return to the starting equation. So if you noticed first, no. So in the first slides here, there was a t, and I was integrating between 0 and t, okay? And so, which is physically sound because it means that when t is equal to 0, basically no previous position are driving the initial condition, if you want. So this equation has an initial condition, whether if you consider this model here, it's something like you add infinite paths that are located in 0, okay? And so it seems like a detail, but you will see in the analysis that it is actually not. And I will make this precise later. And so during the talk, I will try to compare capital X and small x. And what I will call the convolution case is the first equation, and the non-convolution case will be the second one. Okay, so the difference seems minor, but you will see that it leads to very interesting questions. And so, why is it a convolution case? Is that, why the first equation, I call it the convolution case, is because basically the integral term can be split in one part that does not depend on age, so that you recover a constant in front of x of t. So it's alpha mu is where mu naught is the zero order moment of rho. Okay, is in front of x of t, so which means that basically you can apply the Laplace transform. And if you integrate between 0 and t, then you have a product of two functions that depend on time, and a Laplace transform is then useless. Okay, so this is the major difference. And so usually in the Volterra setting, you use the resolvent, which is a kind of fundamental solution, so that if you know, if you characterize well the behavior of the resolvent, then you can characterize the behavior of the solution. So knowing the spectral decomposition of the resolvent is something that is enough to characterize the solution. And so basically this is what I will do here. And of course, in this case, it's important that it's a convolution equation, because in this case, I will use the Laplace transform, okay? And so basically what I will do, I will try to decompose the solution in a singular part and a regular part, or a vanishing part, which will be in L1, okay? And so how do you do this? You use the Laplace transform, and you try to study first the characteristic equation, and I will just show how you obtain this characteristic equation. So when you take the equation and you apply the Laplace transform, it's some because of the initial condition, you will have 1 as a source term, and the Laplace transform of the resolvent will be multiplied by this expression z minus alpha mu 0 plus alpha, the Laplace transform of rho. And so the game now is to characterize the zeros of this characteristic equation, knowing only that, I mean, with the less possible information on rho. And so if you remark that rho naught is equal to mu 0, then you see immediately that z equal to 0 is a solution. And so why this is a problem? Because you're just sitting on the line where you want to invert the Laplace transform. Okay, so if I sum up the result that I will explain later, there is these 3 regimes. One where you are in a weakly repulsive or attractive regime, where the spectrum is just located on the left of the imaginary axis, and you have just one single root in 0, so it's a simple root. You have a critical case where you have the same situation, but your root in 0 is double. And you have the exponential case, so the supercritical case, where you have 2 roots in the real part of real imaginary part, positive real part, and the rest of the spectrum is on the left of the imaginary axis. Okay, so this is why you see those 3 different behaviors, and it all depends only on the product of alpha mu 1, okay? And so basically once you have the spectral decomposition, you are able to write the singular and the regular part. And once this is done, you fully characterize the, let's say, convolution solution, okay? And so what I will present in the next slides is how from this analysis, this spectral analysis, I can compare the non-convolution to the convolution case. And I will show that also the non-convolution case is following the same, is having the same behavior in the subcritical and in the critical case, while for the supercritical case, and that's what was very puzzling, they don't coincide. So basically, it seems that you have the same rate of explosion, let's say the same exponential rate, but that the constant or the expectation of x does not have the same constant in front. And a big challenge, which is still an open question, is to be able to characterize this constant as a function of the data, okay? Because here you see all those constants here that you have in front of your resultant, they only depend basically on the moments, the respective moments of the kernel. So those constants, if in the convolution case, they are fully explicit, okay? So it depends on the source term and on those quantities, okay? And the question is, if you take a non-convolution case, is this the same? Because for the two first case regimes, it is actually the same leading order term, but it's not for the last one, okay? And so now I will just give a few details about the spectral analysis. So when you decompose so you say, I have a characteristic equation. This is a complex function. It's equal to 0. So I will take real and imaginary part. And so in the subcritical regime, what you can show is that the imaginary part is a kind of monotone function when you put yourself on one vertical line, and that the imaginary part cancels only in 0 because it's monotone. And so then you study the real part of f, and what you can see is that it's increasing along the real axis. So basically what you say is that as the real part cancels only in 0, it cannot cancel elsewhere. So there is no 0 in the positive real part. Okay, so this is for the subcritical case. In the critical case, it's a little more technical, but basically the same idea applies, except that the 0 is a double root. And for the supercritical case, what you can show is that the real part is a convex function, that in 0, the real part has a negative derivative, so it's convex, it's negative. The one of the 0 has a negative slope, so it's coercive, and so it shows that basically there is only one positive root. And what you can show is that the real part here is x maximal on the real when the imaginary part is 0. So basically there is no other root between 0 and z0. And above z0, it's exactly the same argument as in the subcritical case. So basically this kind of arguments are enough to, and basically behind all these derivatives, you always find somehow the derivative of f is related to alpha mu1. So basically that's how it works. And but this is just the computation of the roots. This is not the inverting Laplace transform. And inverting Laplace transform, and you have a root on the line where you invert, that's a rather technical task. And so one of the interesting points in the article that we just submitted is that basically it's possible to invert the Laplace transform in this situation. And here, for the subcritical case, this is the computation that you obtain. So basically, you can recover a vanishing function and some constant. And so I will just briefly give the ideas of how you obtain such results. You use local analyticity. And there is a very nice paper by Jordan, Stephens, and Wheeler, which is a kind of toolkit for Laplace inversion in this case. It's very well written, and you can use quite easily the result that you find inside. And also the Bible for the Volterra equation, where you can find some reference to this article as well. Okay, so this in the subcritical case gives you the diffusive behavior of the solution. because then you just have to convolve the resolvent with the source term, which is the Brownian motion. Okay, and so in the supercritical case, you apply exactly the same tools, and you can show that your solution has expectation t to the power 3 halves. And again, in the supercritical regime, still you have a root of 0, but you have another root inside the positive real part. And again, you have an explicit characterization of the solution as a function of the Brownian motion and something that comes from the equation itself, from the kernel itself. And you see here, this quantity now is positive, although this quantity is negative because we are in a super critical regime. Okay. But, and this is a physical drawback, you put a lot of weight on 0 in this case, which means that in the attractive case, it's like you have a lot of linkages that attract you to 0. In the repulsive case, it means that for an infinite time, you have a lot of repulsive forces that come from this attachment to 0, okay, at the initial, at t is equal to 0, okay? And so the non-convolution model, from the physical point of view, it has a real meaning, and that's why we were also interested in this specific model. And so the problem is that in the non-convolution case, you cannot apply a Laplace transform. So the idea was to be able to compare the non-convolution case with the convolution one. It's just that in the repulsive case, I mean in the weakly attractive case, you have either the weakly repulsive forces or attractive forces. So, and in both cases, you don't use the same comparison principles, okay? So that's why I'm going to detail these two steps. So if alpha is negative, you have what you do is you compare the solution, you make the difference, and you have some rest. So, and the rest depends on capital X that you already characterized very well, so you know how it behaves, and you have just a source term to take into account. Okay, and so in this case, and because K here in the claim of the lemma is positive, and in a Volterra equation, the sign of the kernels are really, really important. So you change the sign, everything change. I mean, the behavior changes. So here, the comparison principle is only available if K is positive. Okay. And in this case, you can compare the solution, and it is not, I mean, it's the most easy of all the proofs that we made, because then you can construct a super solution quite easily, and this gives you this comparison between capital X and, so you can do this trajectory by trajectory, then you take the expectation and you obtain this result. So why this result is interesting? Because here you see that it is only a bound. It's not something that goes to 0. It's because X and capital X is behaving like a Brownian motion. So it's already something that in expectation has a behavior like a square root of t, which means that with this estimate, you just ensure that you have the leading order of your solution. I mean, that small x behave like capital X. But you don't control the rest, okay? And so it does not work, of course, if now you alpha becomes positive, because this does not apply. And so in this case, you have to reformulate the problem. So you have a change of a node. So now I define a new variable, which is called the elongation, and that I can show that I can close basically the equation with this new variable. And this looks like a specific gross fragmentation equation with a kernel that does not depend on the external h variable. So here, I'm just integrating with respect to one variable, but this does not depend on the variable that is outside the integral. So it's like a fragmentation term that does not depend on which size you're looking at. Okay, so the particular case, the particular domain that on which I'm considering this solution is a kind of, it's not the Quaternion plane, it's the cone. And so this is also interesting from the, let's say, theoretical point of view. And so I will use this to reformulate the problem and to be able to estimate, to give some new estimates. And for this specific problem, the existing tools that do not work. Okay, so because the domain is not truncated, so the equations are not conservative, and okay, there are some problems. And so if you try to do a spectral analysis, you find that the eigenvector is 0. But close to these ideas, we found a kind of invariant in this case that was quite useful. And with this invariant, we were able to give some stability estimates. So basically, what we were able to do is to use the dissipation of some invariant, of this invariant quantity, to obtain a bound. So this is a dissipation term, which exactly corresponds to a term that is inside the equation that we are interested in and that we want to bound. Okay, and so basically this invariant and the fact that in front of the dissipation term there is 1 minus alpha mu1, which is strictly positive, guarantees that this term is integrable, okay, in time. And so basically then after, when we return to the first known, which is our comparison between x and capital X, okay, we have already bound this term, and we remain just with some bound of the source term. Okay, so this is the trick. And I mean, and you see it's not a specific, I mean, it's not the conservation, it's some kind of dissipation that does the trick. And so, again, you are able to bound the difference, the expectation of the difference by a constant, leading to the same result, but from a totally another way of solving the problem. Okay, now if you look at the critical case, this no longer works, because basically the term that is in front of your dissipation term is vanishing, so that you don't have the control of the same term inside your equation. And so you have to be a little more smart, because then you have to rephrase the equation that you obtained, I mean the estimates and the equation that you obtained with U with this new invariant quantity, and to use a comparison principle, because now your this new invariant basically gives you an operator that has the correct sign. So this is basically what does the trick in the critical case. And I don't go too much into detail, but what you obtain is a bound that again is very narrow, because the expectation of the super diffusion is now t to the power 3/2. And what you have as an error estimated c times t. Okay, so again you see that it's you are just capturing the leading order, but you cannot do much better. Okay, and it is already quite involved to obtain this. So now the supercritical case is an open problem. I don't have any idea how. And if we return to the error estimates, maybe it will be clear why it's. So this is my error, okay? And if now this guy behaves like an exponential, you see that the source term is worse in the error estimates than in the equation itself, where you have a Brownian motion here. Okay, so you see, you compare something and the source term starts to explode. So and also small x is exponential, but somehow the equation does not provide much information. Okay, and so in this specific case, I don't know how to do, but we have some explicit solution when the kernel is decreasing exponential. And in this case, you can do computation both in the convolution and the non-convolution case, and at least try to check if things works like the intuition says. Okay, so in this case, you can compute the resolvent either in the convolution or the non-convolution case. And this is what the resolvent looks like in the non-convolution case. So in the non-convolution case, so the representation formula looks like small x of t is equal to r of s of t integrated between 0 and t of dws. So you integrate with respect to the s variable, okay, and t is fixed. And while capital X is, like we said before, is the resolvent t minus s dws. Okay, so you see that basically rt minus s has to be compared to rs of t. And you see that in the, so maybe I did write the exponent, okay, so I mean, what is puzzling is that basically if you compare those two quantities, the only term that are different is that here you have normally the full integral of the zero order moment, and here you don't have this term. So basically that's the only thing that makes the difference between the two resolvents. And when you look at the limit when t grows large of this resolvent, you find that exactly it has the correct rate, but the constant is different. So the conjecture is true for this specific case, where the kernel is exponential. And you can compute the expectation of the rescaled solution explicitly. And basically, if you do some numerics, you find in the subcritical case that thing works exactly like they do. So this is the difference, and you see that it's less than a constant and not better. if you take the critical case, you see that the difference between x and small x is exactly of order t. Okay, and if you look at the supercritical case, then the simulation do not say anything because as you are computing solution for very large times, you don't trust exactly the output of the numerics, because numerical errors can grow sufficiently large so that the difference tends to a constant, although it should tend to 0. Okay, so but basically it seems to be to go to 0, at least from my point of view. Okay, so if I just sum up, what's puzzling is that the three regimes do not compare fully, especially in the supercritical case. So the nonlinear case is certainly better taking into account for this supercritical regime, because maybe this is not physically sound that the solution blows up in this way. And that's it. Thank you.